So, hi, this is Partha Mishra. First of all, I would like to convey my heartfelt gratitude to all to the Indonesian Journal of Electrical Engineering and Computer Science. And secondly, I am very thanks and grateful to Honorable Editor and Editor-in-Chief, respected Editor-in-Chief and Editor, for giving me such opportunity to present my research paper to this presentation. And finally, I would also thanks to all the reviewer, and I convey my sincere thanks to all the reviewer. They give me such significant comments to improve my manuscript. I acknowledge their comments, and finally, I revise my paper with best of my knowledge and best of my efforts. So I'm going to present my research paper. My research paper title is Machine Learning Based Stator-winding Fault Severity Detection Induction Motor. So title already shows you that my research paper is based on stator-winding interturn fault and of the induction motor by applying machine learning tools. Myself, Partha Mishra, Assistant Professor, College of Engineering Management, Kolhapur, in the Department of Electrical Engineering. Before giving my lecture, so this is I know that induction motor have a wide application in industry, and their failure can lead to significant financial losses. Now, degradation and failure in turn insulation in the winding of the stator of the three-phase induction motor are referred as a stator winding fault. And in this paper, my outline of the talk is uh, introduction, objective of the proposed research work, workflow diagram of the proposed fault diagnosis method, methodology, result and discussion, conclusion and future work, and finally the references. I give a few references of my research paper. So let's start the discussion. First of introduction, as I told you, that induction motor is nothing but a work force, power of any industrial application. It is widely used motor in industry. So the problem is that if any stator winding interturn fault, a minor number of fault occurs, then it is it is inevitable to detect earlier so that we can avoid the losses, financial loss, and complete shutdown of the motor. So this is mainly occurred due to the continuous operation under robust industrial condition. The different stresses may develop, and due to this, that this interturn fault may occur. Uh, so it is very important to detect and classify this fault at the early stage. This is the key. This is the main important, fact of this research, that early detection, so that we can avoid the financial losses and complete shutdown of the motor. Now, these are the different type of induction motor fault. Here we mentioned that electrical fault, mechanical fault, mainly mechanical fault occurs mainly bearing fault, centricity fault, and electrical fault, stator fault and rotor fault. Here, my discussion part is that the stator fault mainly the interturn fault. That means in between this turn, okay, and in these two turns there is interturn short circuit fault occurs. And my research area is this. Now, as I already told you the objective, so similar thing is again, and here it is mentioned that so we should choose a significant technique. There are a number of technique already proposed in by the different researcher. But here, in this research paper, a very simple and simple method has been proposed. So the proposed technique is developed based on the analysis of three-phase stator current only. Only the three-phase stator current we capturing, and this method has been proposed. This modern signal processing and advanced classification tool has been integrated under controlled laboratory condition to develop the proposed fault diagnosis technique. Okay, this is the very simple method, free from complex, burden of calculations, so complexity. So this is the very simple tool. Okay. Now, next slide is that this is our workflow diagram. Here you can see that the design and development of a customized experimental setup. This is the setup where we artificially we create, interturn fault condition. There is number of, we brought out you know, this windings, phase windings, and then artificially we create the interturn fault condition in our experiment. And then the sample thickness current signal data acquisitions technique, and then we use the discrete wavelet transform technique, second level, and then inverse discrete wavelet transform, and then reconstructions, applying the reconstruction same phase current signal. The one important thing is that elimination of fundamental frequency component is essential, because they doesn't make any role for this research. So first of all, we have to eliminate the fundamental frequency component, and then after that we reconstruction the signal, current signal, by using uh, discrete wavelet transform technique, decompositions. Then reconstruction signal by using IDWT, and 50 statistical features extractions from each phase reconstructed current signal. And finally, we use this modern techniques, modern classifier technique that I already told you, that ECOC technique. Here are this technique is very simple, and it is very efficient for our analysis purpose. This is the technique we use as a machine learning technique. Error correcting output code, or it's called ECOC, error correcting output code, support vector machine. So this is the technique we are using. This is the experimental methodology. The experiment was carried out on 2 HP 320 volt 3-phase 50 Hz induction motor with customized stator connected star winding, and then it is coupling with DC generator. This coupling with DC generator with 2.2 kilowatt to 30 volt, 12.1 ampere, 1500 RPM. Fitting part to group of lamp. Here, this is electrical load is only lamp load, and there are 5 load condition: no load, load 1, load 2, load 3, load 4. We're using in our analysis. And finally, the experimental configuration included 3 signal phase transformer, a eco make power meter, and a PC. So all the captured signal we transmitted to the PC for our further analysis or data processing. See here the experimental setup. This has been given. The setup is this is the generator motor coupling set, and lamp load, data acquisition, uh, power meter, all has been given here. Now methodology, as I already told you, that first of all, in this process, capture signal sampled at 20 kilohertz frequency have been decomposed up to 7 level using discrete wavelet transform, which is a multi-resolution signal analysis tool, DWT. Then reconstructed of the same signal without 50 Hz frequency, because this 50 Hz frequency we have to eliminate. It doesn't make any role. So has been implementing IDWT, the Inverse Wavelet 2 has been used, and significant changes in magnitude and shape of the reconstructed phase current waveform may be noted due to the change in fault condition. Thus, the reconstructed signal may carry potential information related to fault or operating condition of the motor. So here you see that this reconstructed Y phase current waveform obtained at healthy and significant changes is clearly visible. So there are healthy 2-turn and 4-turn cases in Y phase, reconstructed Y phase current waveform obtained at healthy and 2-turn and 4-turn no load fault condition. So no load 2-turn and 4-turn fault condition, you can see the change, the variation changes. It is clearly shown. These are the statistical features that we are using here. So these 15 statistical features: mean, maximum value, root mean square, RMS, square root mean, standard deviation, variance, shape factor, SRM shape factor, then sixth moment, fifth moment, kurtosis, skewness, impulse factor, attitude factor, twist factor. These are the formula here it is given. Then result and discussion part. So in this result and discussion part, a total 45 features were extracted. Well, 45 features were extracted, 15 features from each of RYV. These 15 features are already shown in this table. Most of these features were found to have reasonable variance with change of the operating conditions from healthy to highest possible fault condition under the scope of the present study. We have implemented successfully, and in next slide you can see that the bar plot which shows the change of the operating condition from healthy to highest possible fault condition. So after a close observation on all extracted features, it could be noted that all the features are pertinent and include information about the operating condition of the motor. So machine learning algorithm to be trained effectively to make it more robust. So after when in a reconstructed signal, we are from reconstructed signal we extracted these 15 features. These features has a significant information, and these 15 features are used here for our analysis. See this these figures is at least because negative value has been given, that's why it looks like this. And now this 0L means no load, 1L, 2L and 3L and 4L is this the load condition. There is 5 load conditions. So the mean value of R phase reconstructed current under different case studies. So in this has been plotted. So from 1-turn, 2-turn, 3-turn, 4-turn, 5-turn, 6-turn cases. This is the mean value. Similarly, in shape factor value, we are using here. So in these cases also, we see the shape factor value of Y phase reconstructed current under different case studies. Next is the kurtosis value of B phase reconstructed current under different case studies. So in different case studies, you see the kurtosis value. Now this classifier that they are correcting, as I told you, this ECOC classifier aided by SVM. It is error correcting output codes. Error correcting output codes aided by SVM implemented in MATLAB platform. So 7 operating case, 106 different interturn fault conditions were considered in this study. Each operating case was carried out at 5 different loading conditions. Each experiment was repeated 4 times, since in the total there were 7 cross 5 cross 4, 140 observations. All the 140 observations were used for training and testing phases of ECOC-SVM classifier. And this error correcting output codes support vector machine classifier is used here. And out of that, 70% observation are taken for training and 30% of observation were used for testing. But training testing is required for the identification. And now this is the result has been shown here. During test phases, the trained model exhibits reasonably good fault detection accuracy. The result obtained from the proposed classifier model has been presented in the form of confusion matrix. So see the confusion matrix. So result has been given here. So this in this case, the correct classification have been shown by blue boxes. The correct classification have been shown by blue boxes, and the misclassification are shown by pink boxes. The correct classification has been shown in blue boxes, and the misclassification has been shown by pink boxes. It may be noted that approximately 94% classification accuracy would be achieved. It may be noted that 94% classification, classification accuracy have been achieved and could be achieved in our system, in our proposed research work. So conclusion and future work. Conclusion is that is a conventional statistical approach was implemented in wavelet-based reconstructed time series current signal for early detection of interturn short circuit. The proposed technique could be accurately detected interturn short circuit for involving very few numbers of turns, that is minimum 0.28% of the total turns in a phase winding, which in turn make it unique. That means very minimum number of turns, 0.28%. So this is unique analysis. The proposed method also established the detection of minor number of faults under varying load level. As I discussed earlier, that we have 5 load level, no load 2, load 4. And this different load level, we also the minor number of turns, the 1 turn to 1, 2, 3, 4, 5, 6 turn we have discussed earlier. So varying load level which make the proposed fault analysis technique load independent. The normalization of three-phase current at the initial stage of the analysis make the extractor statistical machine independent. So also machine independent. That means that in high rating machine also we can use our technique. They achieve 94% classification accuracy, which is while classifying different severity of interturns of circuit, fault in highly satisfactory. Now, in our future study, you can say that it may be implementing this interturn short circuit faults with unbalanced supply voltage and partial insulation fault in stator winding. We can implement it, we can consider it in our future study, future scope. These are the few references here I mentioned. And thank you. Thank you for being with my presentation. Thank you.